All right. So in this video, we will basically take a closer look at the conservation laws that exist in this theory of electromagnetism, and so we'll start to discuss various conservation laws, and one of them we have already seen before, which is the charge conservation. But apart from that, we will also discuss the energy conservations, the momentum and angular momentum conservations in this video. So let's start again with the basic equations, which are these Maxwell's equations. And so I have purposely written them in this form. Now you know the reason why. These equations, which are the equations without sources, these equations are essentially solved, or they are identities if we write the electric and magnetic field in terms of the scalar and vector potentials. Whereas the equations with the sources, with the charge density and the current density, they need to be solved, and we solve the potentials, the scalar and vector potentials in terms of the charge densities and current densities. And in the previous video, we saw once we solved those potentials, we could find the electric and magnetic field for an arbitrary given charge density and current density, and those were the Jeffrey-Menko solution. Okay, so now we will do a lot of lot more analysis with Jeffrey-Menko solution, but in this particular video we will pause a little bit to uncover a few more structural aspects of this theory, and these are related to the conservation laws. So of course, apart from the Maxwell's equations, we also have the Lorentz force equation. So basically here, this is the expression for the Lorentz force on a point charge q, and we can write this in terms of a force density. So if you take this force density, which is written in terms of the charge density and the current density, and if we integrate it for a point charge, then we get back this expression. This Lorentz force equation is also one of the fundamental equations, and is a part of our starting point. So good. So given the Maxwell's equations we have seen before towards the beginning of this lecture series, that we can manipulate the Maxwell's equations and obtain this conservation of charge. So I have told you that you can view this as a consistency condition on the sources which essentially source the electric and magnetic fields. And so this is a local statement of the conservation of charge. Of course, if we integrate it, then we get it converts into a statement of conservation of charge within a particular volume. So we can do the volume integral on this equation. So this equation follows from the Maxwell's equation. In some sense, it is contained in the Maxwell's equations in a way. So, but again, as I have mentioned before, and we'll see also later, that there are some deeper symmetry reasons for this equation. There are very interesting symmetry reasons behind this particular conservation law. And in any case, the equation of motion always has these informations about the conservation laws. Okay, so just like the charge conservation, the equation of motion also has information about energy conservation and momentum conservation and angular momentum conservation. Okay, so in this video, we will try to explore that. And it is also true that these energy, momentum, and angular momentum conservation, they follow from some symmetry arguments. Okay, but so we will revisit these conservation laws when we have done the Lagrangian formulation of electrodynamics. But before that, in this particular video, I want to develop this more as a I want to find these conservation equations starting from this equation of motion, or these field equations themselves. And basically, we want to develop a little bit of a calculational handle on how to deal with these conservation equations, and what interesting things that this can tell us about various physical situations. We'll try to explore that in this video. Okay, so yeah. So basically, we'll start with the so-called Poynting theorem. and which is nothing but an expression for conservation of energy. Okay. So again, our just to motivate the starting point, our starting, you can consider a single point charge in some electric and magnetic field, okay, which can be created by other moving charges. If it is if this point charge also has its own electric and magnetic field if it is moving. So, the force that this point charge would experience is given by the Lorentz force law. And so if it is moving around in the electric and magnetic field, then the amount of work done by the electric and magnetic field is given by the force, the Lorentz force dot dr, where this dr is basically the displacement vector for the point charge q. Okay. So this so if the point charge is, let's say, moving with some velocity v, it's an instantaneous velocity v. So if it is moving with some velocity v, then this f dot dr, which is basically this infinitesimal work done dw, let's say it is we are considering an infinitesimal time, which is delta t, and the work done on the point charge in this time interval delta t would be given by this Lorentz force q times E plus v cross b dot dr. This displacement vector is nothing but v times delta t. Okay, if this is the infinitesimal time interval. Okay, so therefore the rate of work done is simply given by q times E dot v, because this expression v cross b dot v, this simply vanishes. Okay, so this if it is like a cross b dot a, this kind of thing vanishes. If you have any doubts, again, write it out in terms of the epsilon ijk, and you will see that the antisymmetry of the epsilon ijk can be used to just argue that this term is zero. Okay, this is the same reason why people say that magnetic fields do no work. Okay, so basically the magnetic field doesn't have any immediate contribution to the immediate or direct contribution to this work done, but as you will see, it will play a role. As you will soon see, this is going to play a role. So because again, as you know, time varying magnetic fields can create electric fields, and that can play a role here. So so basically we are considering a most general charge configuration. Let's say, there are some moving charges, but they are localized, that is what we are going to consider. Okay, so now if we take this step, we can say that, we can convert this work done for a point charge into the work done for a local charge density. And then, so basically, this rate of work done, we can convert it into the rate of work done per unit volume, and then integrate over a given volume which contains these charge densities. So if I convert this Q into a charge density, then charge density times volume, that's going to give me the current here. So this expression is nothing, this rate of doing work is nothing but the volume integral of E dot J. So this E dot J has the interpretation of a density. So it is basically the rate of work done per unit volume. And so if I integrate that, then I'll get this rate of doing work. Okay, so it is the rate of doing work by the electric field on the charges. And we'll also assume that if we integrate this over some volume V, then we are going to assume that the charges that are involved, or the charge configuration that is involved, they don't leave these volumes. So essentially, as I said, we are going to consider localized charge and current densities. So we can always consider a volume which is bigger than the region in which the charge and current densities are localized. So in that case, there is no charge and current density which is leaving the volume. So that will be there. We are going to assume that. Okay, very good. So if we assume that, then we can do some algebraic manipulation on this expression E dot J. We can now do some algebraic manipulations using the field equations, or using Maxwell's equations. We'll do some algebraic manipulations on this E dot J. So to start off with, we can substitute the J using Ampere's law. Okay, we know that Ampere's law is nothing but, again, is nothing but what? Curl of B equation. This is the curl of B equation. curl of B, basically this is curl of B minus 1 over C square. So, right, let me write it as, let me write it as mu naught epsilon naught del E del T. And this is equal to mu naught times J. So here you can just use this to solve for J. You can use this to solve for J and plug it in here and plug it in here. Okay, you can just use this to solve for J and plug it in here. So take this J and plug it in here. And once you do that, then what you get is basically two terms corresponding to these two terms. The first term is E dot curl of B, and the second term is E dot del E del T. Okay. So now, of course, so this term is quite simple, but let us try to again reanalyze that what is this term. Okay. So we'll just again do some algebraic manipulations here. So this is the divergence of, so let's first start with the divergence of E cross B. Okay, so if you start with the divergence of E cross B, I have written it down in the index notation. So there's the index of this derivative contracts with the curl index. So it's del I, this I is summed over jk, and this j is summed over, this k is summed over. Okay, so this is the expression in terms of the indices. So now we can just readjust. We can take the derivative and act it on E. Okay, then there will be del I ej. And we can also take the derivative and act it on B. Okay. So if we do that, then there are these two terms where we have just acted the derivative. So this is like a product of two terms, and we have acted the derivative and written it as two separate terms here. So if we do that, we can identify this equation here as simply, again, we can take the k in front. So this is nothing but B dot curl of E. Okay, this becomes B dot curl of E. And again, here also, if we take the j and put it in front, then I have gone across just one index, and therefore that is going to give me a sign. So this is going to give me minus ejik, minus epsilon jik ej del I bk. Okay, so basically now you see this one, this part becomes the curl of B. Okay, because this is ik here, and then it is dotted with E. So the sign comes out from the algebraic manipulation of the indices. Okay, so basically vectorically, so finally we can write this also vectorically. So vectorically, this is an identity that the divergence of E cross B is given by this expression here. Okay, so very good. And as we have seen, so here there's this E dot curl of B, and that is, E dot curl of B, and that is given here, out here. This is also E dot curl of B. So basically E dot curl of B can be written as this term divergence of E cross B, and this is equal to basically minus of this and plus of this. Okay. So now if we now try to write down this E cross B also using Faraday's law as minus del B del T. So we can put in the vectors here, which I have missed. So if we write this in terms of del B del T, then this term can also be written down simply as, this expression can be written down as minus B dot del B del T. This is by Faraday's law. This by Faraday's law becomes del B del T. The minus sign is here. And so we have finally arrived at this particular identity. Okay. So with this particular identity, we can use, so basically in this identity, I have taken this on the left hand side and took this on the right hand side. And then, so this is the one that appeared in the E dot G expression here. Okay, so we substitute that using these two terms here. Okay, we just substitute it here and we get this expression. Okay, so here, therefore we see that there are three terms now. All the terms have minus signs, so I'm pulling the minus sign out. And then we see that these two terms, this one and this one, they fit together as a time derivative of this term, which is basically E square plus B square, apart from the epsilons. It's half E square plus B square with the right epsilon and mu naught to make them dimensionally consistent. Okay, so this expression here you have seen before. individually you have seen that this was the energy density in the electric fields in electrostatics, and this was the energy density in the magnetic fields in magnetostatics. And basically here, this particular expression also appears in a very interesting and suggestive form. You see, here what we are seeing is basically this thing is basically related to the work done on the charged particles. Okay, that is related to the time derivative of a quantity here, and then it is also we also have this another quantity here, which is basically the divergence of E cross B. Okay, so just first just appreciate, try to appreciate the similarity of this expression here, of this local expression here, with the current conservation equation. Okay, so if there is no work done, for instance, if this is 0, okay, then this expression here reduces to an identical expression like this, where this, instead of the charge density, you have this expression for E and B, and instead of the current density, you have this expression in terms of the E and B fields. Okay, so this equation has the interpretation that this object here is nothing but the energy density in the electric and magnetic fields, and this object here is basically nothing but the energy current. So this may be a new concept. Okay, so this is the energy current in the E and B fields. Okay, so now it's similar to the charge current. Okay, it's very similar in spirit to the charge current, but this says that the electric and magnetic fields can not only have a energy density, but it can carry energy current and move from one place to another. Energy can move from one place to another through this energy current in case of just electric and magnetic fields. Okay, so basically now if we put them together, so the rate of work done, now we have to integrate E dot J. So this E dot J is integrated, and we have these two expressions here. Okay, this is the time derivative of a quantity, which is the energy density, and the divergence of the energy current. Again, sorry, I have missed a factor of, I can see I have missed a factor of 1 over mu naught here. Okay, so good. So now, therefore, as I said, so this is what the expression is, and this expression here is known as the Poynting theorem. Of course, if you have a volume integral here, then because this is the divergence of a vector, you can use divergence theorem to convert it into a surface integral. So this is the surface of the volume in which you are interested in, or in which the charges are enclosed. So that is the surface of the volume. Okay, so it's the bounding surface of the volume. Okay, so basically it's a closed surface. This one is a closed surface. And so this has the following interpretation, that if you have a given region where there are some charges that are moving around, and you take a bigger region and you integrate it, integrate the amount of work done, the rate of work done, compute the rate of work done on the charges, and then basically the rate of work done on the charges, is as you do work on the charges, the energy in the electric and magnetic fields, they reduce, and that's why the minus sign. Okay, so basically the work done on the charges, on the charged particles by the electric and magnetic field, that reduces the energy density in the electric and magnetic fields, and so that's one way. And the other thing is the energy in the electric and magnetic fields can also relieve the region via the energy current. Okay, so if you have a region, then there are some charged particles here. The electric and magnetic fields can do work on the charged particles, or leave this region through the surface as in the form of some energy current. Okay, and that these two processes contribute to the reduction or increase in the energy density of the electromagnetic fields in that region. Okay, so that is the interpretation of this Poynting theorem. Okay, so now you have these two nice quantities, which is the energy density and the energy current. This expression for the energy current, it is denoted by this S. This is often called the Poynting vector. Okay, this is the popular name for it. It is also sometimes referred to the energy flux density. Okay, that is also referred to as this. But just by analogy with the charge conservation, we can think of this as the current density. Okay, it's energy current density. Okay, so yeah, so energy current or energy current density. Right. So let me just modify this energy current density. Okay, this has the interpretation of energy current density, which can leave through the surface and move away, and thus reduce the total electromagnetic energy density in the region. Okay, so the total electromagnetic energy in the region, right? If we do the volume integration. Okay, so but in the absence of, let's say, there is some electric and magnetic fields in some region, you're doing something, and there are no charge particles on which they can do work, then basically this term, this goes to zero, this goes to zero, this is zero, and if this is zero, then we have a local statement of energy conservation, and this UEM is the energy density, which is given by this expression, and this divergence of S is basically the energy current density, and this expression is exactly the same as the charge conservation equation. Okay, so this is the statement of energy conservation in the electric and magnetic fields. So as you can see, the electric and magnetic fields, they are entities on their own. They have a charge. They can have a they cannot have charge, but they can have energy density. They can have an energy current, and that energy in the electric and magnetic fields can flow from one region to another. So it's a living entity on its own. Okay, so very good. So right. So I should also emphasize the fact that in magnetostatics you have seen that it's just E squared. Half E square, and in electrostatics you have seen that it's half E square, and magnetostatics you have seen that it's half B square. And so in a situation where you have electrostatics and magnetostatics together, the energy density had to be E square plus B square, half of E square plus B square. That had to be the case. But that expression is more general than just a combination of electrostatics and magnetostatics. Even in a dynamical situation, as we have seen here, the energy density is given by half of E square plus B square, and that is what we are going to use we can use that in any dynamical situation, and we can get the right results out of it. Okay, very good. So this is something which is very important, and so this is how it is. This is one of the so basically, therefore, this equation, or more generally, this equation, Poynting's theorem, this is a statement of conservation of energy in a system where you have charges and you have electric and magnetic fields together with some charged particles. So this is the most general form of the energy conservation statement. All right, now let's move on to the next topic, which is conservation of momentum or linear momentum. Okay, so for this, let us look at the expression for force. Okay, so we know that now, we have used it many times, that the force is given by the integral of a force density, which is given by this expression. Okay, so this expression, again, this rho times V, I can write as the current density J. Okay, so this is the expression, and we can take this expression and integrate it over some volume. Okay, now what volume we are going to integrate it over is basically our choice. Okay, so we can integrate it over any volume, and we'll get the force on the charged particles within that volume. That is the idea, right? So basically, let's say we have a charge distribution like this, which is colored here. Okay, this is the whole entire charge distribution. We can try and select a volume which is a part of this charge distribution, which is this hemispherical, this filled hemispherical region is the volume, let's say. Okay, this is the volume V, and we can take and integrate it over this volume. Then this expression is going to give us the force only on this charged objects which are contained within this volume. It will not compute the force on this. It will not take into account the force on the charged distribution which is outside the region. Okay, so again, this is something very interesting and also very important, that we can do the integration over whatever volume we like, and it will give us the force on the charge and current configurations inside that volume. Okay, that's the point. Okay, so now let us take again this density expression and let's try to do some algebraic manipulations on this expression for the force density. Okay, so let's start here. The charge density here, we can use Gauss law to write the charge density as the divergence of the electric field, and we can use Faraday's law. Sorry, this is not Faraday's law. We want to write down the current density in terms of the magnetic field and the electric field. So that is done by Ampere's law with the Maxwell correction. Right. So this is the Ampere's law, and we have converted the charge density in terms of the. So it's a local equation that has to be valid, and therefore we can just use it here. That it's valid point by point. So the the current density here can be substituted by the magnetic field and the electric field at that point of interest. Okay. So this is we can use Ampere's law to do the local form of the Ampere's law to do that. Okay. So this is the first step. In the second step, what we can do is, of course, this term remains. This is the Gauss law term. This term remains, and here these two terms split into there are two terms like this. One is this del E del T cross B, and the other one is curl of B cross B. Okay, curl of B cross B. Okay, that is the next term. Now it's time again to do some manipulations, algebraic manipulations. So if we start with E cross B, and if we take a time derivative on E cross B, then we see that the time derivative can act on B as well as the time derivative can act on E as well as it can act on B. So we'll get two terms. Okay, here it has acted on E, and here it has acted on B. Now this term will let it remain as it is. But for del B del T, we use Faraday's law to convert del B del T into minus curl of E. So we get a E cross curl of E out here in this expression. We get a E cross curl of E. Okay, so as you can see here, so we have a here also, if we flip the sign of this object, then we'll get a B cross curl of B, and here also one term is generated which is E cross curl of E. Okay, so now, and as you can see that this expression del E del T cross B is identical with this expression. So we can think about substituting this expression in using this one, this term, and this term. Okay, that's what we are going to do. So this is the, I have written this on the left hand side, and so group together the terms on the right hand side. So basically I've taken this on this side. Okay, so both terms are plus now. Now again, so basically I'm plugging back this term here in this expression for force density. I'm plugging it here. I'm plugging it here. So once I do that, what I see here is basically what I see here is there are lots of terms here, right? So of course there's this del del T of E cross B, which I keep separate. Okay, with the sign. There's a minus sign here, and I keep this term separately. Okay, and then after that there are these four terms. There's this term, there's this term, and then there's this term. This term is not there, right? This term is not there, but as you can see, this term is there here. Okay, and this E cross B, this one I have written here. There was a minus sign, so I have taken the minus sign inside, and then here I have flipped. So this was curl of B cross B, so that I have flipped. I have written it as B cross curl of B with the sign, and that also can be written here. Okay, that has the right sign. And just to make this equation look symmetric in terms of the E and B fields, we can put in another term which is divergence of B divergence of B times B. So this is divergence of E times E. So we can put in another term which is divergence of B times B. And this we can do because, as we know by the Maxwell's equation, this divergence of B is always 0. Okay, so we have just added 0 to this expression, and that will not change anything. So we can do that, and we are doing this just to keep this expression in this form and to make it look symmetric in terms of the E and B fields. Okay, if this is 0 and we don't write it, then this expression has two terms and this is one term. But just to make it look symmetric in terms of E and B fields, we have written this term here. Okay, which we can always do. We can add a 0. Doesn't matter. Okay, so now again we look at these individual terms. Okay, E cross curl of E and B cross curl of B, and we try to use an identity. So this is something we can use. So E cross curl of B would be given by half of gradient of E square minus E dot nabla acting on E again. Okay, so how do I see this? So I worked this identity out for you here. So basically the ith component of this expression, that will be given in terms of the epsilon. So for this first cross, I've written I, j, k, and this E has this j index, and this vector will have the k index. But then I can write this out again. I have written epsilon. So this is the k index that has come here, epsilon klm, and then this del will have the L index, because this is the curl, and M index will be carried by this E out here. Okay, so that's how I have written everything out. But now, as you know, there are two indices that are identical and summed over in the epsilon, and in that case, you can use the product of two epsilons to write in terms of the deltas. Okay, that makes it simplifies the expression. So if I try to do that, so I've just shifted this k, let's say, just to take it in front, and so that I can apply the identity. And this will not cost me a sign because I've shifted it across two indices here. Okay, because I've shifted it across two indices, this is not going to cost me any sign. And therefore, I can apply this identity in terms of the delta function here. And once I apply the identity in terms of the delta function, this is given by this is given by this this I have kept the same as here. Okay, now let us perform the index let us use the delta functions to sum over indices. Here we see I is L, this is the Kronecker delta. So here L is this L index is there, and I is the free index here. So basically this derivative will get the free index, whereas J and M is summed over, so this will get summed over. Okay, so this J and J becomes the same thing. And in the next term, the I index goes to M, so the I index goes to this electric field inside, and J and L is summed over, so basically these two terms are summed over. Okay, so in terms of indices, this reduces to this, and again, because this is Ej del I Ej, therefore I can take one Ej inside and use a factor of half, because this will again have two terms which are identical. Okay, so that if I reduce it by half, I'll get back this. Okay, so this, and then now if I write it in this way, you can see that inside this is just E square, and this derivative has the free index, so this is the vector index of the gradient of this. So this is carrying the I index, the free index, and here in this next term we have this E dot del, because this J is summed over, so this is E dot del, and the free index I is carried by the electric field, so this vector is basically the vector which is this entire vector. Okay, that vector index of that vector. Okay, so basically we have this identity now, which we can use back in our force density equation and try to see where we can go with that. Okay, so I have done this manipulation for the electric field, but I haven't used any Maxwell's equation in this manipulation. So the similar manipulation also holds for the magnetic field, and I can write down the cross product of B cross curl of B in the same way as E. These are identical expressions. Okay, so let's use these two expressions back in the expression for force density. And if I do that, there are these two terms that are appearing, and for these two terms, I just substitute here this. So both of them has a minus sign, and these are two terms with one with a minus sign, one with a plus. So the one with the plus becomes minus in these two cases, and the one with the minus becomes plus here. Okay, So this is just a simple substitution back into that expression. And once we have this, then I want to write this whole expression in terms of indices again. Okay, so there's some very interesting feature hidden in this expression, which will become apparent once I write it in terms of the indices. Okay, it's very difficult to see when written in terms of in the vector notation. Okay, but if I write it in terms of the indices, there's something very simple and very nice which is hidden in this expression, and that is going to become apparent. So let's try to do that. So again, the ith component of this, if I consider the free index to be the I index, so that is the ith component. Okay, this is the index which is not summed over, so this is free index. So this is given by here, again, these are the two indices that are summed over. So this is the divergence of the electric field. So del J, Ej, it's summed over, it's the divergence. And the free index is carried by E here. And similarly here, in this case, the E is dotted with this J, and the free index is carried by the electric field here. And then minus, this is delta J. I have put in delta J because here the derivatives have the J index. So, following that I have put in delta J, but here the derivative carries the free index, I index. Okay, so I need to put in a Kronecker delta Ij to make this delta, this del J, to make that del I, because that should be del I typically. Okay, so that to make that into del I have introduced this Kronecker delta del Ij. So if I sum over J in this expression, I will immediately get del I, which will reduce to this expression here, because I is the free index here. Okay, so I hope the steps are clear now. Similar exercise is done for the magnetic field part as well. But as soon as we do this, we realize that, you see, these two terms we can write together in this form. Okay, why can we write it together in this form? Because this is a derivative, jth derivative. Okay, this is del of xj. Okay, and that can act on these two ej, ei. So again, because there are two terms like this inside ej, ei, so this is something like, let's say, ex, ez, something like that. So therefore, this derivative can give me two terms when it acts on this expression inside. Okay, so the first term will be this term, when it will give me the divergence of E. The first term will be this term. And the second term, when the derivative acts on the EI, this will give me this term here, because the EJ will come outside, and the EJ is dotted with the nabla, or the derivative. Okay, the J index is summed with EJ, and then I'll get back this term. So these two terms together is identically equal to this expression here. Okay. So similarly, the magnetic field is the same manipulation here, is identically equal to this expression here. Okay, it's the same manipulation. Very good. Now, if we look at this now in this form, we see that there is a derivative on every term in this expression out here. Okay, so we can pull the derivative out. Okay, and then inside we have a quantity which is a two-indexed quantity, because it has a J index and it has an I index. You've already encountered such two-index quantities before in the form of a quadrupole moment. So these are like, two vectors written side by side in some sense of the word. Okay, so as you can see, the two vectors E and E is written side by side. Again, you can have other structures as well in the form of the Kronecker delta Ij. So it's a two-indexed quantity. Okay, so it's a two-indexed quantity, and this quantity out here has a name. It's called the Maxwell stress tensor. Okay, it's called the Maxwell stress tensor, and this is one of, again, a very, very fundamental quantity involving the electric and magnetic fields. Just like we've seen, the energy density is a fundamental quantity, the energy current is a very important and fundamental quantity. So is this combination of electric and magnetic field which forms the Maxwell stress tensor. Okay, so if we now define it in this form, Tij, this is denoted, this is standard notation for the Maxwell's stress tensor. If I denote it with Tij, then this is the complete expression for the Maxwell stress tensor. And as I said, it is very similar to in spirit, it's very similar to the quadrupole moment, although, there is no direct connection as such. I mean, here we are doing a completely different thing, but I'm saying the index structure is similar to the quadrupole moment. That's what I mean. Okay, so now therefore compactly we can write down this ith component of the force density as del j tji, this term here, and we can write it as del t of epsilon naught times E cross B. So you see there was this epsilon naught times E cross B here. Okay, this is the ith component of that. So that term would remain here, and here we have to put in the ith component of this. So the I component is a free component. Here j is summed over. Here j is summed over. So therefore we see that again here this force density has the same form as the current conservation or the energy conservation equation. Okay, just that it has an additional index now, because here also there is the force density is a vector, so this has an additional index now, and it is basically del t of another vector, and this is in some sense the divergence of another quantity, which of a two-indexed quantity. Okay, it's the divergence of a two-indexed quantity, and so this is often this can often be written this two-index quantity, just like a vector you put a single arrow, you can put a double arrow here, and that will represent the two-index quantity Tij. Okay, this is a compact notation sometimes used. Okay, again, if you go to a three-index quantity, then you run out of ways to show the arrows. Okay, but so this is like a double arrow. So if you now this term here is nothing but this double arrow with one index contracted with the so this is yeah. I wish I have written it in a cleaner way. Let me try to write it in a cleaner way. So this Tij is sometimes denoted with a double arrow. This Tij is sometimes denoted with a double arrow, and right, and this and here this term here sometimes with this compact notation you can write as the divergence. This is also a divergence, by the way. Okay, this is the divergence of this double index quantity. Again, here when I'm talking about the indices, I'm thinking about Cartesian coordinates, and I'm thinking about the components of these vectors and these double index quantities, which are sometimes referred to as tensors. So these vectors and tensors, I'm thinking of their components in the Cartesian coordinates. Again, I'm in Euclidean space where I can always choose these Cartesian coordinates. So these are the components with respect to the Cartesian coordinates. And compactly, this is often written in this form. This divergence of this quantity is often written in this form. Okay. Now you see, here we have force density. Now we see here we have force density. And because this is force density acting on the charged particles, this will determine the rate of change of momentum or rate of change of mechanical momentum of the charged particles. Okay, this is just Newton's law. Okay, so this is the rate of change of mechanical momentum of the charged particles, and because of this reason, this object here that we have written down, del t of this object here, this object is now considered in this expression. This object is considered as the momentum density. So momentum is a vector. So momentum density is also a vector, as you can see from here. It's E cross B. It's again E cross B. Okay. Earlier we had seen that momentum density earlier we have seen that the energy current density was E cross B, 1 over mu naught though. But here, the momentum density is also E cross B. So this momentum density, if you say electromagnetic momentum density, momentum in the electromagnetic fields, that is 1 over, c square, the Poynting vector. Okay, this because the factors of epsilon naught and mu naught are just different. Other than that, it's just E cross B again. Okay, very good. So this, you see, therefore, these two are identical. These two quantities are identical. The one thing, E cross P can be interpreted in both ways. It can be interpreted as the current density or the energy current density, as well as it can be interpreted as the momentum density. Okay. So now this momentum density is the momentum per unit volume. Okay. But as you know that when you are interpreting this as the current density, this has the right unit of current density. Okay. So this is and that unit is basically taken care by this multiplication with the mu naught, or division by the mu naught, and multiplication with the epsilon naught. Okay, the units are taken care. Okay, and the most interesting thing is this Maxwell's stress tensor that we have written down, that has the natural interpretation of current momentum current density. Okay, so this, if you can think as momentum current density. Again, think of this expression. You think of your conservation equation. Okay, del T of rho plus divergence of J. So basically, the divergence of J here, this T executes the role of J, and this this vector here executes the role of rho. But you see, when it was a rho, then the current was a vector. But when the density itself is a vector, then the corresponding current is has two indices. Okay, so it's a tensor. So very good. And essentially, what it means in terms of Tij, what it means in terms of the electric and magnetic fields is basically this expression here. Okay, that's all you need to care at the moment. Okay, don't think about vectors, tensors, etc. Just think of know how to do calculations with this. And so this is in Cartesian coordinates. This is the way in which Tij is written, and that is it. Okay. So so very good. So this is therefore this statement together now, therefore you can think of as the as a statement of conservation of momentum. Okay. So basically, because this is a force density, F, small f is a force density, then we basically have this ddt of momentum density. This is also mechanical momentum density, if you like. Okay, this is mechanical momentum density. Okay, it's density because everything is per unit volume, so it's density. Okay, so now you can always find the total mechanical momentum. This m here stands for mechanical. Okay, so the total mechanical momentum is nothing but take the mechanical momentum density and integrate it over a given volume. That will give you, if you do the, there are I particles, let's say moving with velocity v, then this will be the mass of the particles times the velocity. If the masses are different, then you can also put a I index here. Okay, if the masses are if the masses of the charged particles are different. Okay, so this is nothing but mechanical momentum, and so this is total mechanical momentum in the charge configuration, which experiences the force, and this is the this can be written in terms of a momentum density integrated over volume. Okay, so again, so therefore the local statement here is the following. The local statement here is the following. This should be, again, because this is the local statement, I should write partial derivatives here. Okay, and as I said before, this EM, so EM stands for momentum in electromagnetic fields. Okay, so this is electromagnetic momentum or electric and magnetic fields momentum. Okay, that has a single index I, this has a single index I, but this Tij has a double index, and this is interpreted as momentum current density. Again, sorry, let me correct it. Momentum current density of the EM fields. Okay, this is interpreted as momentum current density, momentum current per unit volume. This thing. Okay, it's the current density, corresponding current density of EM fields. Okay, so now we can take the local expression and integrate it. So if we integrate it, then this will be the total force. Okay, this will be the total force. And the total force is basically equal to ddt of the total momentum, because now we have integrated and we can take the volume integration inside the time derivative. So this is the total momentum, and this is total momentum, and this is equal to minus the momentum, which is in the rate of change of momentum in the electric and magnetic fields, which is E cross B. Okay, this is momentum density integrated over the same volume V. And this expression here, again, something very similar happens. It is the volume integral of a divergence. Well, it's not the divergence of a vector. It's, even after taking the divergence, it is a vector. That is the point. But it's a volume, again, nevertheless, it has the same structure of the divergence of a vector, because these J indices are summed over. So the the divergence theorem can be applied to this term as well, and this term can be converted into a surface integral, okay, where this index J is contracted with the normal vector to the surface. Okay, so this J index is the vector. So ds vector is the area element including direction for the surface, which encloses the volume V. So this is the closed surface. Okay. And this is the area element on the surface including the direction, and because it includes the direction, it's a vector, so that vector has a J index, and that J index is to be contracted with the I index. So let me just remind you what happens for the usual divergence theorem. Usual divergence theorem is del J, let's say some J, okay, this is volume integral, okay, this is equal to, so basically when this volume integral, so this is volume V. Okay, so this is the surface of, this is a closed surface. Okay, S equals to the boundary of the volume V, and sorry, it's the boundary of the volume V, and this we have to take the ds vector and dot it with Vj. So we'll write a dsj Vj. So that's the usual divergence theorem for you, written in the vectorial notation, written in the component notation with the index notation. And similarly, this thing also applies for this term here, which we can write as a surface integral in this form. Okay, and this is a super useful form, that the fact that we can convert this into a surface integral. Okay, note that in a static situation, so in a static situation where this ddt of the electric and magnetic fields are not changing. By a static situation, I mean let's say the electric and magnetic fields are not changing, and the force, therefore the total force, would be essentially given by this surface integral of this Maxwell's stress tensor. Okay, so in the static situation where, let's say, there is something else which is also binding the charges, not letting it move to produce time-dependent electric and magnetic field. So in such a situation, this term is going to go away, and the total force on any charged particles inside a volume will be given by a surface integral, where that surface is a closed surface enclosing that volume, and it's a surface integral of the Maxwell's stress tensor. Okay, and as you can see, this sign here cancels, and this Tji has the same expression that I wrote down initially in terms of the electric and magnetic fields. This is the expression for Tij. Okay, and the one thing to remember, and this is very interesting and important, it's so important that I should write it down. Okay, Tij is symmetric in Ing. Tij equal to Tji. As you can see from this expression clearly, okay, Tij is equal to Tji. This is going to be very important. Okay, the fact that the Maxwell stress tensor is symmetric in its indices. Okay, all right, very good. So now let us do some examples. So this is the statement of the conservation of momentum, linear momentum, and now let us do some examples. Okay. The first example we are going to focus on is basically this static case that we have. There's a very interesting example which is given in Griffiths. So if you look at page 368 in Griffiths, you will see that this example has been worked out there, but it is a very instructive example which I want to discuss so that you get the idea here, what is going on. So here, what they have asked us to do is to consider a perfectly spherical ball of charge. So there's a uniform charge density and the total charge is q. Okay, the total charge is q, so there's a uniform charge density. If you integrate the uniform charge density with the volume of the sphere, then you will get the total charge, which is q. Okay, if you multiply the constant charge density with the volume of the sphere, that's the total charge q. Okay, so this charge is distributed uniformly. And we have to find the force. So basically there is electric field everywhere. Okay, there are electric fields everywhere. There are electric fields even inside. There are electric fields. Okay, even in points inside there are electric fields. Okay, and these electric fields create forces. So there are charge particles here and there is an electric field here that will create a force on these charge particles. Okay, and therefore there will be, if you vectorically sum all these forces, that will give you the total force on the charge particles. And let's say we are interested in finding the total force on the northern hemisphere like this. Okay, we are interested in finding the total force on the northern hemisphere. So if you are interested in finding the total force on the northern hemisphere, what do? We can take find the individual forces, the electric fields at every point, and multiply them with the corresponding charge density and then integrate over the volume. So that a volume integration that you guys can do and you can test or find what the answer is. Okay, so that's one volume integral that you can do. But here, what we want to do is a different thing. We want to use the Maxwell's stress tensor to find the answer. Okay, that's what we are going to do. Okay, so this Fn is basically the force on the northern hemisphere, and the symmetry of the problem tells us that this force will be directed in this direction. Okay, in the upward north direction, because everything is plus. So it's going to repel. And now the symmetry of the problem tells me the force on the northern hemisphere should be in this direction and the force on the southern hemisphere should be in this direction. So there should be something in addition to this electric forces that will try to keep this thing together. Okay. So that's the thing, and that additional thing exists, let's say, so that everything is a static case, and we have static electric fields, and we have static charges. Okay, so under that assumption for this problem, if you want to compute the force on the northern hemisphere, then let's do it in the first way, which I'm calling take one. Okay, so in this take one, what we are going to do, we are going to consider the volume which, we are going to consider a volume which encloses the northern hemisphere. So it's basically the surface of the northern hemisphere and plus this little disk, which is the equatorial disk. So in the equator, you draw a disk like this, and this is the equatorial disk, and on top of it, you have this surface which bounds. So this surface of the bowl, like, the hemispherical bowl like this. So that surface and this disk together forms a closed surface, which is the northern hemisphere. The entire northern hemisphere is contained within these two surfaces. Okay, so we can take this surface and find the Maxwell's stress tensor and try to evaluate what we find for the Maxwell's stress tensor, the surface integral of the Maxwell's stress tensor here. And as we have seen before, in this particular static case, this surface integral of the Maxwell stress tensor would give me the total force. So I don't have to do a volume integral, I just need to do a surface integral, and the electric fields at the surface kind of knows that, whatever is inside and tells you the force that acts on whatever inside. Okay, so this is some super nice and super, magical thing that is happening here. Okay, so you see, for the charged sphere, we know what the electric fields are everywhere. You can, because this is a symmetric situation, so you can draw your favorite Gaussian surface and find what the electric fields are. But if you are now an expert in writing down the solution in terms of the potential, then you can find the potential, and then from the potential you can calculate the electric field. This is also possible. So if we do all of that, in fact, in your assignments, you have done a very similar problem in the problem set, where instead of a solid sphere, you know, it was a more complicated problem. It was like a scooped up sphere. You know, it was like a spherical shell where another sphere from inside was scooped out. Okay, so that is a slightly more difficult problem, but this is an easier problem. So here you can write the electric field inside in this form. Okay, there's a 1 over r cube. Okay, and where this r is the this distance here. Okay, it's the radius of this sphere. Okay, and this r is the point where you are finding the electric field. Okay, this is the r vector. It's the point where you are finding the electric field. You can find it anywhere. It's the corresponding r vector that we have here. Okay, and then the region outside, you know, there is no charge outside, and as you can see, if you draw a Gaussian surface, then it's given by the charge inside, and then it's just Coulomb's law, which is just this expression. Okay, and it's always pointed radially outside because it's a uniform charge distribution. There's spherical symmetry, so it is the electric field is always pointed radially outwards. Okay, so now you can just take these expressions, and we want to find the force on the northern hemisphere by evaluating this integral on the surface S1. Again, remember the surface S1 is a combination of two surfaces. One is this hemispherical surface, and the other is this disc-like surface at the this circular disc-like surface at the equatorial on the equatorial plane. Okay, so that we have to find this integral. Now here, just for simplicity, we will use a physical intuition. As I said, that the force on this northern hemisphere would be acting along the z direction. Okay, it's going to be acting in this direction, and this one will be in this direction. Okay, so because the force will be in the z direction, therefore this I index here, the free index I, we can just make this free index I into a z index. Okay, that's what we need. Okay, it's a z component of the force. That is the one that is going to be non-zero, and by symmetry, the x and the y components are going to be 0. And if this is z here, this goes and becomes this index out here in t. So basically, this j is summed over for the surface integral, but this free index is j because the force, we are interested in finding the force in the z direction. Okay, very good. So now we look at the Maxwell's stress tensor and see what it tells us. So basically, the components that we need here, therefore, are if you like, we need basically txz, tyz, and tzz. Okay, so these are the three components of the Maxwell's stress tensor that we need, because j runs over x, y, z. Okay, 1, 2, 3, and that is because this index is just z. Therefore, we need only three components of the Maxwell's. We need just three components of the Maxwell's stress tensor. Okay, so let's evaluate those three components. We know also the electric field behaves in this way. We know the electric field inside and outside. We know the forms of the electric field. Sorry, we know the forms of the electric field inside and outside. So let's say but this bowl or this region that we are interested, this is just at the radius r, right? It is just situated at the radius r. Let us say that it is situated infinitesimally outside. So we will use the outside electric field to find what is there. What is the Maxwell stress tensor here on this hemispherical dome. Okay, so if I try to find that, then if you look at the expression for Maxwell's stress tensor, then it has the magnetic fields. This configuration doesn't have any magnetic fields, so this term just vanishes. And here we have these two terms, which are the electric fields. And here you see we have a delta ij. Okay, because we have a delta ij, you see the xz component, this is the component that we need. So that will just be Ex, Ez, so this term will contribute. But here, because x and z are not the same thing, okay, so this will be delta xz, and that is equal to 0. So this term is not going to contribute in this expression. Okay, similarly, Tyz, this term is going to contribute, Ey, Ez, But again, delta yz, that's 0. So this term is not going to contribute. But for tzz, this term is going to contribute, of course, because it will become ez square. Okay, now this term here, this is zz, so this is equal to 1. So this is e square, but this is half e square. So I can write this as ex square, ey square, ez square, because this is the e vector square. Okay, in terms of Cartesian components, I can write this as ex square, ey square, ez square. And because there is a factor of half, this ez square will reduce this, and we can pull the factor of half outside. So ez square will appear with the plus sign, whereas ex square and ey square is going to appear with the minus sign because the sign is minus here. Okay, that's the algebraic manipulation. And here, right, here we can see the following, that so here, because we have written the, we are going to consider this outside electric field. So the outside electric field has this expression. Okay, so the Ex, Ey, Ez are basically XYZ component of this r hat vector. And this r hat vector, as you can see, the r vector is basically this full vector. So if you remove this r from here, then it simply becomes r hat. So these are the components of the r hat vector, the x component, y component, and the z component. Okay, so it's very easy to write down what the corresponding values of the electric field are, and this is divided by r square. But on the hemispherical surface here, that radius r here is simply capital R, right, on the hemispherical surface. So because this r is capital R, therefore we can simply write this ex ez, this term on the surface r equal to capital R. Therefore we have substituted small r square as capital R square. Capital R square is the radius of the sphere. Okay, and it's also the radius of the hemisphere that we are considering to integrate. Okay, so that if we take this now, and we just, here I have just used the fact that these come from the r hat. Okay, these terms come from the r hat. So you just take them and multiply it, ex, ez. Okay, so as you can see that, let's see, so sine theta cos phi, this comes from the ex, whereas this cos theta, this comes from the ez. Okay, so that's how, and this factor is common, so it just gets a whole square. Okay, so similarly you can work out this txz, tyz, and tzz. The tzz is again slightly more complicated. You can work it out and find that this is given by cos square theta minus sine square theta. Okay, so again you put in what this z, x, and y, all these things here, and then you will see what you get. Very good. So once we get that, then we want to perform the integration of this quantity on the surface, on the hemispherical dome. And the area element on the hemispherical dome, because it's the surface of a sphere, then the area element is, so this is the dome, right? So the area element is pointing in the radial direction outside, and the area element is, because this radius is capital R, so this is r square sine theta d theta d phi. Okay, that's the area element on the surface of the hemisphere. So now all we have to do is to take the x component of this area element, y component, and z component, and multiply it with the corresponding components of the Maxwell stress tensor, and we'll get the answer. So there is an r hat here. You have to be slightly careful because there is an r hat here. So the r hat has non-trivial x, y, and z components. Okay, that you need to consider. Okay, in terms of theta and phi coordinates. Okay, spherical polar coordinates. The r hat vector has important components which you must take into account. Okay, so now putting everything together, dx, txz. Okay, there's of course there's a factor. There's this factor which is common to all these terms, all the three terms. But I have only kept track of the angles here. Okay, I have only kept track of the angles. So if I keep track of the angles, I can see that I have to, like, this dxz, for instance, that is given by 1 sine theta, 2 sine theta, that's sine theta square, and cos phi. So that's sine theta square cos phi, we can see from there. And apart from this, there is also txz. Txz has sine theta, cos theta, sine phi. Okay, so with this, you have to multiply sine theta, what was it? Sine theta, sine square theta cos phi with this sine square theta cos phi. Okay, so that will make it sine cube theta sine cube theta cos theta, right. That is going to make it sine cube theta cos square phi. Okay. So one cos phi comes from this r hat here in the area element, and the other cos phi is basically present here in txz. Okay. So similarly, we have just I've just kept track of the angle terms. That's why I put the tilde here. If you multiply this by this factor, then this is like a exact result on the hemispherical surface. And so this is on the surface, small r equal to capital R. This is the expression. And now we need to add them up. So if we add them up, this simplifies, and it simply becomes, at the end of the day, it simply becomes half of sine theta. Right, it simply becomes half of sine theta cos theta. Okay, there is no phi dependence. The phi dependence is gone in the algebraic. For instance, if you add this and this, cos square phi and sine square phi, they add and give you 1. So the cos dependence is just gone. Sorry, the phi dependence is just gone. And we are left over with the theta dependence, which also simplifies to this simple form. Okay, so take this factor of half and put it in here, and then put in this factor, the right factor. Okay, that factor also has been put in here. Okay, and then sine theta cos phi d theta d phi. So the d phi integral is going to give you a 2 pi, because on the surface of the hemispherical dome, phi goes from 0 to 2 pi, but theta goes from 0 to pi by 2. So it's the angle with the z-axis. It goes from, so z-axis, this angle is basically pi by 2. So this is 0. So this is 0 to pi by 2 for theta, and phi on the other hand, that goes on for the full 2 pi rotations. Okay, so very good. So we can take this now and try to perform the integration. And if we try to perform the integration, because phi goes from 0 to 2 pi, there's a 2 pi factor here, and this sine theta cos theta, well, of course, if you integrate it over 2 pi, that vanishes, but because you're integrated over pi by 2, this, I think, gives a factor of half here. So because this gives a factor of half, as you can see from here, so there's a whole square, this half cancels, so there's an additional 4 here, this epsilon cancels, and the pi cancels, 1 of the pi. So if I write down as 1 over 4 pi epsilon naught, then there's a factor of 8 from the product of this 2 with this 2, or if you like, the product of this 4 and 2 that remains, and these 2 cancel. That's how the algebra works out. So this is the contribution to the force which comes from integrating only on the surface of the hemisphere. Now we have, this is not the full answer, because we also have the bottom of the hemisphere, which is this disk. So we also have to find and integrate the Maxwell stress tensor on this disk and find the contribution of that to the total force on the northern hemisphere. Okay, so we need to do that. So if we want to do that, then we have to find the Maxwell stress tensor on the disk. So that's the first thing that we have to do. So on the disk, firstly, the area element on the disk is basically given by this term here, which is basically, this is like a circle. So this is R dr. So sorry, this is like a circle. So this is R dr, and basically, if you like, this is d theta. This is d theta. This is dr. So this is d theta dr, and it's pointing in the z direction. Typically, if it is in the usual way, but we want it to point outwards, so it is pointing in the minus z direction. Okay. So this, this volume, we want the vectors on the surface to point outwards from the volume. So the vector on the upper surface pointed in the radial direction. Outer, this hemispherical surface, the vector pointed in the radial direction. But for this surface here, this disk here, the vector should point in the negative z direction, which is what we have done here. We have taken the area element to satisfy. We have taken the area element to satisfy this expression here. Okay, this is the natural element on the disk. Very good. Also, the electric field inside, that electric field inside is equal to this expression. So this is the r vector, the full r vector, including the value of r. Okay, but we are interested to find it on the disk, where I guess theta is equal to pi by 2. Okay, if theta is equal to pi by 2, the sine pi by 2 that gives you 1, but the cos pi by 2 that gives you 0. So basically you are left with only the x and the y components. The z component vanishes. So the z component of the electric field vanishes on the disk. So if you consider again this disk, okay, here on the disk there is no z component of the electric field. It is always pointing in the direction of x and y axis. Okay, I hope this is clear. Here on the disk means at theta equal to pi by 2. Okay. So now basically because the electric field is outside and it just has the z component is is 0. Therefore, because the z component of the electric field is 0 and this Txz, as you remember, is Ex Ez, because this z component is 0, therefore it is 0. And similarly, this is proportional to Ey Ez, and because again this is multiplied by the Ez component, which is 0 here, so the Ez component is 0. So in particular, Ez is 0 here, and that implies that these two required components of the Maxwell stress tensor, they just vanish because the Ez component of the electric field vanish on the disk. It doesn't vanish everywhere, but on the disk it vanishes. At theta equal to pi by 2, it vanishes, and therefore this can be a very good. So this simplifies life a lot. But the ZZ component does not vanish. The ZZ component is given by this. Again, this part vanishes. Okay, this part is equal to 0. So this is Ex squared plus Ey squared. And if you look at the E, Ex squared plus Ey squared is, gives you sine squared theta sine square phi cos square phi, cos square phi sine square phi, and that adds to 1. Right, that adds to 1, and then we had this factor of half outside, so this is epsilon by 2, and the minus signs were there, so the minus sign is outside, and then you have to multiply with this factor twice, so that's q by 4 pi epsilon naught r cube twice. So here I think I have written this formula wrong, because if you see that this is the electric field inside, as we discussed before, is given by it's given by r cube, capital R cube in the denominator. So because this is a capital R cube in the denominator, I think I have made a little error here. That will be capital R cube. Okay, this will be capital R cube. This will be capital R cube. Okay, so if this is capital R cube, then again you see the error got corrected in the next step. Okay, so this is capital R cube, and so basically, Ex squared Ux squared will have this term squared from both the pieces, and this is capital R cube, and now this is equal to R square. Now what is R square? R is the radial distance. So here it's the radial distance on the disk. Okay, that is R. Okay, that R square will remain. Okay. So if this R square remains, now putting things together, so the only component that is non-zero here is the Z component of the area element and the TZZ, which we just evaluated here. So the Z component of the area element, what is that given by? The Z component of the area element we have evaluated here. It's just R d phi dr. Okay, with a minus sign because it's pointing in the negative Z direction. So therefore, right. Right. So therefore, here the two signs cancel. This sign and the fact that the area element points in the negative Z direction, they cancel, and so this is the expression now. And from here we have a factor of R square, and from the area element we have a factor of R. So this is R cube and R cube dr d phi. And so for phi, we integrate again from 0 to 2 pi, the same thing on the disk. But for the disk, this r is the radial coordinate, so we integrate from 0 to capital R. Okay, so we can just take this expression and perform that integral. If we perform that integral, we'll see that there's a 1 over 16 in this particular expression. So putting everything together, we see that the force on the northern hemisphere, so this is Fn, and the Z component of that, that is the only non-zero component. Okay, you can check if you have enough patience. You can check the other components. They will come out to be 0 because the symmetry of the problem demands that. Okay, so you can check it in this way. Okay, directly you can check it in this way. If you say x component here, you have to set x and then find the relevant t. You know, you have to find txx, tyx, tzx. Okay, and some of this term you have already found because it's symmetric. These two terms you have to find, and then you can check that identically would vanish for when the when we consider the full integration, both the surfaces, then we will see that those components, the x and y components, they vanish. Okay, so now this S1, as we saw, had two pieces to it. There's a hemisphere dome. Okay, hemisphere dome. There's a hemisphere. And then there's this equatorial disk. Then there is this so this surface S1, if you remember, this surface S1 has two parts to it. This is the equatorial disk. This is the equatorial disk. This is what I'm calling the equatorial disk. And then there's a hemispherical dome like this, okay, which is also there. Okay, this is the hemispherical dome, and this is the first integral. Okay, let's call it let's call it A1, and let's call it A2. So this is A1 and this is A2. Okay, we just did these two integrals. So one had this 1/8 factor and the other had the 1/16 factor. So overall you'll get a 3/16 factor, q square by r square, this thing. So this is the total force acting on the full northern hemisphere. And as you can see, we didn't need to do a volume integral. Just from the surface, we could figure out what the force on the current configuration inside is. Now, from this analysis, you might think that we have to consider a surface that just encloses the current configuration, because this is what it did here, right? So the current configuration, so the charge configuration or the current configuration fitted in exactly within the hemispherical dome, and you might think that is necessary, but I have to emphasize that is not necessary. Okay, for instance, if you have this surface here, sorry, let's say there's some configuration, sorry, there's this circle, this spherical configuration. This is the problem that we have. You could have chosen a surface like this. You could have chosen a surface like this outside. Sorry. You could have chosen, so basically we want the northern hemisphere, right? We want the northern hemisphere like this. Okay, so you could have chosen a surface like this, which cuts it on the equatorial plane, and it's some dome like this. Okay, even in this case, you'd get the right answer. Even in this case. Okay, you see here the northern hemisphere does not fit in exactly within the volume. So this is my choice of volume. So the northern hemisphere doesn't fit in exactly within the choice of volume. But even in this case, if you were to do the integration, you will get the right answer. So let's do another take on this problem with another surface where we can make this disk, this disk that I have drawn here, this disk, let me paint it with green. So this disk that I have drawn, the equatorial disk, let's make it the equatorial plane, the full xy axis. Let's make it the full xy axis. And then this dome is basically the hemisphere at infinity. Okay, well, that's another surface. Let's try to do the integral over that surface. This I have schematically represented here is the full xy plane. Okay, this is the green thing that I have extended to up to infinity. And then I'm assuming that this one closes, but it closes by a hemispherical dome at infinity. Now, as you know, the electric field at infinity due to this charge configuration vanishes. So the contribution from that hemispherical dome will be zero. Because the electric field vanishes, the Maxwell's stress tensor is expressed in terms of the electric field, and basically the electric field at infinity vanishes. Therefore, the Maxwell's stress tensor at infinity also vanishes. So there will be no contribution from the hemispherical dome, but there will be contributions from the electric field that exists on the xy plane. Okay, so we can do this integration now on the xy plane. Okay, just if we consider the xy plane and do the integration, then we must get the same answer, because this is also a closed volume. Okay, this is the interesting part. So let's see. So here, as you can see on this xy plane, again there are two parts to the problem. One is the region inside, which is this disk. Okay, this region inside disk we have already considered, and we have calculated the integration of the Maxwell's stress tensor on this disk. Again, the surface is pointing in the negative z direction, so let's consider that as the, let's close this on top. Okay, so if we close this on top, we have to do that because we are interested in the force on the northern hemisphere, and that must be contained within the volume. So we have to close it on top. If we close it on top, this by a large hemispherical dome at infinity, then that doesn't get any contribution, but there are contributions from this xy plane points. This xy plane also has two parts to it. One is the region inside the charge distribution, and the other is the region outside the charge distribution. Okay, so the region inside the charge distribution that we have already so this is the xy plane and the hemisphere. Okay, these are the two contributions from this thing, but this is zero because the Maxwell's stress tensor goes to zero at infinity, because the electric fields go to zero at infinity. Okay, so I can write because E goes to zero at infinity. Right. So that's the reason. So now once this term vanishes, we don't need to worry about the hemisphere at infinity. The xy plane itself has two parts. One is this equatorial disk inside, and the other is the xy plane outside. Okay, so this calculation we have just done in the previous take, and this was this result, okay, with the 1/16 factor. Okay, and then now if we try to look at this expression, we have to find this now, which is the xy plane outside. Because it is the xy plane outside, we use the expression for the electric field outside. But now you see, it is not at a fixed value of r, but this value of r will vary depending on where we are on the plane, right? Depending on where we are on the plane, the value of r would vary, right? So basically, this, as we saw, that this integral, when we perform this integral in terms of the r here, so we had to integrate from 0 to r. Okay, the r integral must be performed from 0 to r. So for the integral outside, we have to perform an integral from r to infinity. Okay, so the value of r here, should the small r here should vary from capital R to infinity. Okay, I have written it here. Okay, it should vary from capital R to infinity. Okay, so very good. So once I have so this is, and phi of course goes from 0 to 2 pi all the way. So that will remain. So now this electric field looks like this because of the r hat. This is the r hat vector completely. Again, on the xy plane, theta equal to pi by 2, and therefore the electric field takes a much simpler form. Again, the z component is 0 of the electric field. The z component is 0. And therefore, the only relevant component of the Maxwell stress tensor is the ZZ component of the Maxwell stress tensor. And that ZZ component on the XY plane, therefore, takes the form in this way. It's the same expression. But now you see there is a factor of 1 over r squared, that if you square it, that will become a factor of 1 over r to the 4. Okay, that will become a factor of 1 over r to the 4. And again, the area element, we can keep the same area element pointing in the negative z direction. That's the sign. Okay, now if we just multiply this, we'll have this expression and 1 over r cube. And if we just perform the integration, we'll get this factor of 1/8. So if you just add them together now for the force on the northern part, okay, it's basically this whole plane. Okay, what we have done is, this northern part is here, and we have integrated the stress tensor over this whole plane from 0 to infinity. Okay, that's what we have done. and 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 the idea is that we are going to close the plane off using this hemisphere at infinity, which this hemisphere at infinity contributes to 0, and the plane has two parts to it. One is the equatorial disk inside, that has this 1 over 16, and this part we just calculated now, that has the 1 over 8. If you put them together, you will get the 3q squared by 16 r squared, this thing with the factor of 1 over 4 pi epsilon. That's the same as the answer you get in take 1. Okay, so it does not matter what volume you choose, as long as the relevant portion on which you are trying to find the force is inside your volume and nothing else is inside your volume, you will get the right force. Okay, so if you now extend the volume to, for instance, this is the thing, so this is the sphere, but if you consider the volume to be something like this, which includes some additional elements, so it will not be the right force. It will give you the force on everything, all the charge components. If you do the surface integral, then it will give you for a closed surface, then it will give you the force on all the charge and current configuration inside, enclosed by this surface. Okay, so that's the thing, and that surface can be any surface. It doesn't matter. It will give you the right answer always. Okay, that surface can be any surface. Very good. So that's the thing. That's the lesson that we learned from here. And with that, let me go on to the next example that I want to describe. And this example is very interesting. I find it very interesting, and it's also very mysterious. It will seem to be mysterious to you. I will not be able to clear your mystery right now. Again, we'll perhaps return back to this point later on in the course. So let us see. Let us consider a static configuration. Okay, this is the discussion of a mysterious hidden momentum in the electric and magnetic fields. So let us consider a static charge plus q, which is static, standing there, and a steady current loop. Okay, there is a steady current I passing through this loop. So the electric field that this static charge creates is independent of time. This magnetic field that this loop creates is also independent of time. These charge and this loop are close together, so that there is some overlap, non-trivial overlap between the electric and magnetic fields, which are created by the charge and the loop. Okay, so we have steady current here, we have a static charge here. So basically, this is a system which is electrostatics plus magnetostatics. This system is a system where you can put together electrostatics and magnetostatics. Okay, so the E and the B is non-trivial. So we have learned that the momentum in the electric and magnetic field, or the momentum density, is simply E cross B. Okay, if it is simply E cross B, then this is the total momentum is basically the integration of E cross B. Okay, if it is the integration of E cross B, then we can write E as the gradient of the potential. Again, I have taken into account the sign here, minus of grad phi. Why is it minus of grad phi? In general, E is not minus of grad phi. In general, E is, if you remember, minus of grad phi minus del A del T. That is there. Okay, but again, because it's electrostatics, therefore the E can be simply given by minus grad phi. Okay, so because this is electrostatics. Okay, so this is the expression that we are going to use. So you are going to use all the expressions in electrostatics and magnetostatics. Okay, so this is the expression. Now let us simplify this term. Let us see what is the curl of this quantity, curl of phi times B. Okay, let us see curl of phi times B. And so if I write it again in terms of the epsilon, there will be a derivative. If I write it in terms of the epsilon, there will be a derivative del j k, where this k is this the kth component of this. This is the index which is contracted with this k. And again, the derivative is acting on two things, phi and bk. So there will be two terms, one where it acts on phi and the other where it acts on bk. And the term where it acts on phi, this will be the gradient of phi cross bk, cross b, that I index will just come over. And as we can see, this is what we have here, gradient of phi cross b, this is that term. And then there is an additional term where the phi comes out, the derivative doesn't act on it. And then this together forms the curl of b. Okay, so it's phi times curl of b here. Okay, so now the if we now perform a volume integral over it, so this is a volume integral, so this is the identity that we just derived. But if we take this identity and if we perform a volume integral, then we see that this is equal to 0. Now, why is this equal to 0? The volume integral of this thing, why is this equal to 0? Okay, so if you remember our discussion with the current, we had argued that the volume integral of the current vanished. And our argument was very much general, and all that it needed is the divergence of the current to be 0. Okay, that was the only input that we needed to show that the volume integral of the current is 0 in magnetostatics, if you remember that discussion. Now this vector here is the curl of something. So basically, if I take the curl, if I take the divergence of this thing, the divergence of this vector curl of phi times b, this must be equal to 0 because the divergence of a curl is always equal to 0. This must be equal to 0. Okay, so therefore this vector is a vector which is divergence free, and the volume integral of a divergence free vector is always 0. So this term will essentially be 0. If this term is 0, then this is the term of interest. This can be written as minus of this term, right? This can be written as minus of this term. Okay, so now we can just use this back in this expression for the momentum in this configuration. This is a very simple configuration, right? You know, static point charge and one loop put together. You know, that is the configuration. So if we now have this expression here, so this is there's a minus. There was already a minus sign here, and in this identity also there is a minus sign. So the minus sign goes away, and we have phi of curl of B. And curl of B again in magnetostatics we know is mu naught times the current density. So this is something equal to phi times the current density. You know, that's what it comes out to be. Again, mu naught epsilon naught is 1 over c square, so that remains as 1 over c square. So this is the momentum density. Okay, sorry, this is the total momentum. This is the total momentum. Let me write. This is not the momentum density. This is the total momentum in this case. This is the total momentum in this case, the integrated momentum in this particular situation. This is the total integrated momentum. And in general, this is not 0. In general, this is not 0. Let us see why, you know, a little more explicitly that this is not 0. What we can do is, again, there's a plus charge here and there's a loop here. So we can consider origin somewhere near the loop. You know, let's say this is the origin. Okay, origin somewhere near the loop. And we expand the potential due to this charge near, you know, this origin which is near the loop. Okay, and if we expand it around that point, then of course there will be a phi naught, you know, that thing, plus there's if you like this is the x. Okay, so we are expanding, you know, so this is the, so we have chosen the origin here and the charge is at a different location. So with respect to x we are expanding, so the next term will be x dot gradient of phi, and that gradient of phi is nothing but the minus of the electric field at that point. That's why I have included the naught here, and so on. Okay, so there will be other terms, but again these other terms, as you know, because it can happen that these other terms would also contribute. So what I am doing now is a slightly crude approximation. But you see, you know, these electric and magnetic fields fall off very rapidly away from these charges. So if these two things are very close by, then only you know, that contribution, you know, it contributes to this integral. Otherwise, it doesn't contribute to this integral. Even if you consider a very large region for this volume which contains this configuration, even then the contribution is kind of becomes kind of negligible, because the electric and magnetic fields kind of fall off very rapidly as you move away from this configuration. It falls off very rapidly. Okay, so that is the reason why, you know, this approximation is justified. Now with this approximation, again we are just trying to see that this is non-zero. Okay, that's what we're trying to see. So with this approximation we can write down the two terms. One is phi naught and the other is x dot e naught. And the phi naught term, this is independent of any coordinate, so it can be brought out. Then this again becomes the integral of the volume integral of the current. Again, this current is a steady current, so we are in magnetostatics. So basically this current here, because it's divergence of J, this is equal to 0. So therefore the volume integral of the current is equal to 0. Okay, the volume integral is equal to 0. And so this term is equal to 0. And the next term here we have Ji xj. This we have seen before while manipulating the force expression for force, etc. We have seen that this is given by the magnetic dipole moment of the current configuration. In this case, it's just the loop. So this is given by the magnetic dipole moment in this form in terms of the. So there's the I and J index free index here. There's the IJ index free here, and this K index is summed over. Okay. So this expression we can use back in there, and we can write this in. So this E would be contracted with one of these indices. Okay, this will be X index. So the E will be contracted with the J, and therefore you can use the epsilon to write it as a cross product between this E naught and M. So this will be the leading term in that approximation, and this is definitely not equal to 0. This E cross M, this is some constant, and in the leading, this is the leading term, and this is not equal to 0. Very clearly, this is not equal to 0. Let's say there's some loop here which is where which has a moment like this, and there's a charge here where there's some electric field like this. So E cross M is definitely not equal to 0. Okay, so right. So this thing is not 0, but we are dealing with a completely static case, right? Everything is static. The electric field and magnetic field is static. The current is a steady current, and the charge is not moving. It's a static charge. So basically, this momentum, the electric and magnetic fields still carry momentum. Okay, and if you are looking at momentum conservation, then this momentum should be conserved in the sense that, because in the sense that we discussed a while ago, the conservation of momentum should be there, because momentum can get exchanged only between the electric and magnetic field and the charged particles. There can be exchange of momentum, or there can be a momentum current that carries it away. But there is no current at all also. Okay, so there is no momentum current, and there is no this thing. So basically we want to understand what happens to this momentum. Is there any mechanical momentum that kind of would basically try to is there any mechanical momentum that would try to so basically you see the electric and magnetic fields fall off away from the charges. So if you take the volume to be the infinite space, so at infinity the charges are 0. So the integration of the Maxwell stress tensor at the infinite sphere, that contribution is just 0. Okay, but the volume contribution is still there, and in the momentum conservation equation, the volume contribution is still there, and from the volume contribution we get a non-zero answer. So this must be balanced by some mechanical momentum, right? Otherwise, conservation of momentum is not going to be valid. So this must be balanced by some mechanical momentum. Okay, so now where is the mechanical momentum? Nothing is moving. Where is the mechanical momentum? So you might say that the charges are moving. Okay, it's the right intuition that the charges are moving to give rise to the current. So we should look there carefully. Okay, but as you can see through this naive argument, it's very important that this is a naive argument, that if I take the integral of the charge density, integral of the current density, then for magnetostatics this would vanish. So this will be equal to 0. Also, this charge density is rho times v. If I think of this as rho times v, where this rho are the various charge particles moving in the current, let's say the electrons. So it's basically the electron charge E times the velocity of the individual electrons summed over all the electrons. So this K maybe levels the electrons, and you sum over all the electrons. Okay. So in this sum, because the electron has a fixed E by M ratio, you can divide by M and multiply by M, bring E by M outside the sum and put the M inside. Okay. And then this now becomes mechanical momentum. Okay. This now becomes clearly mechanical momentum carried by the electrons, right? So this thing must be 0 if it gives rise to this current, which is a steady current. Okay. By this logic, this must be 0. So mechanical momentum looks to be zero. And so basically then what happens, what balances this particular momentum, this particular, like this particular momentum in the electromagnetic fields in this particular static case, what balances this momentum. Okay, so that is a little bit of a mystery, and so there's some kind of hidden momentums hidden somewhere maybe. Okay, which maybe cancels out this momentum, and so because this is a static case, nothing moving, so you would expect the total momentum to be zero, right? So somehow something is happening somewhere, which is giving rise, which might cancel out this momentum, right? So basically, so there's something wrong with the logic that I gave you, and so I will leave it again as a food for thought to think about, what is going on here. It's a very interesting situation, but I suspect that you have the right know-how to answer this question at the moment. But see if you can come back to this mystery and solve it once you have learned special relativity and yeah, particularly special relativistic dynamics. Once you have learned that, see if you can come back to this problem and solve this puzzle. That in the static case, the moment you would naively expect the total momentum to be zero, but we see that the electric and magnetic fields even in the static case has some momentum. So why is why is it not equal to zero? Why is the total momentum of the static system not equal to zero? Okay, that is the question. Okay, so there may be some hidden momentum hidden somewhere. Okay, and so that is the mystery I would like to leave you with. Okay, so this is the second example. The third example is a very simple and straightforward example, and that is the example of electromagnetic plane waves, which we have discussed like 2 videos earlier. Okay, so here, let's say we are given a plane electromagnetic wave which is of this form, and so straightforwardly we can compute the energy density in this electromagnetic wave, E square plus V square, and that from this expression we can just compute. So this is a well-defined electromagnetic wave where this omega equal to c times k. This k and omega are related, and also the magnitudes of the electric and magnetic field, they are related. They are also orthogonal to each other, and the wave is propagating along the z direction. That is the plane wave. Okay, now if you consider the plane wave and try to find the energy density in the plane wave, then this is given by E square plus V square, half of E square plus V square. You can take this and compute E square plus V square. In fact, V square is just 1 over C square, this thing. So because V square is 1 over C square E square, therefore you can just take, the C square is mu naught epsilon naught. So these two terms, together forms epsilon naught E square. And this becomes epsilon naught E square cos square. This cos square comes from this cos thing here. When you square it, you get a cos square kz minus omega t. Okay. So this is the expression for the energy density. This is the expression for energy density. Now it is very conventional in these kind of situations to consider something which is the average energy density, where by average I mean it is the time average of energy density over one complete time period of this wave. Okay, so this time period is 2 pi by omega. So if you take this t and integrate it from 0 to t in time, and then divide by 1 over t, okay, that is the time, that is like taking the time average over one time period, and that expression, so this cos square, whenever you integrate cos square over one complete cycle, you just get a half. Okay, that's a very important result. If you remember this, you will find it super useful. Okay, cos square integrated over one cycle is half. It doesn't matter what multiplies it, you can check it explicitly, you can check this integral. This is going to give you a factor of half. Okay, so this average energy density in the electromagnetic wave is half epsilon E naught square. It's proportional, the average energy density is proportional to the amplitude square of the electromagnetic wave. Okay, very good. So that's one thing. The second thing is we can see that what is the energy current or the energy current density carried by the electromagnetic waves. So this we can say that this is the energy current density. So the energy current density is given by the Poynting vector. This Poynting vector has this form 1 over mu naught. So the Poynting vector has 1 over mu naught and E cross B. So here also, because E and B are orthogonal to each other, so I cross J is K, and so this is along the Z direction. This is K. I mean, this is K. This is K. And of course, it's the same magnitude, so it's basically right. E squared cos squared this thing. So there's a 1 over mu naught, but there are factors of there's a factor of C in B as well. So I think here what has been used. So there's a factor of C coming from this B. So I think we have used C times epsilon naught is equal to 1 over C times mu naught. Okay, this has been used here, and then you get this expression. Okay, so so now if you take the time average again over one period, you only get a factor of half from this cos square integral. So this is half C epsilon naught E naught squared, and this energy current is pointing along the Z direction, and the energy current density is basically this expression here. Okay, so this energy current density has the interpretation as it is the average power. So average because it's the time average over one period. So it's the average power. Power is again energy per unit time. That average power per unit area. Okay, that is transported by the electromagnetic waves through a surface orthogonal to the z-axis. So this expression out here, this magnitude, is the average power per unit area transported by the electromagnetic waves through a surface orthogonal to the direction of propagation of the plane wave. Okay, and this is what is defined to be the intensity of the electromagnetic wave, and this intensity is therefore given by this expression here, which is given by the intensity is given by the average energy density. Okay, so this is a measure of the power traveling through the electromagnetic wave per unit area. Okay, so that is this thing. So this is the intensity, and the next thing to consider is the momentum density. Okay, and the momentum density is the same thing. It just has a difference of this factors of epsilon naught. Okay, it's the same E cross B. It just has a difference of factors of epsilon naught. So for the current, for the energy current density, there was a 1 over mu naught, but here there is a epsilon naught. So you can just adjust them to write it as 1 over C squared times the Poynting vector, which we just evaluated a while ago. So the factor of C will cancel from the numerator. So this will be 1 over C times epsilon naught E naught squared, this thing. So again, if you take the time average, this will just give you a factor of half here, which is half times C E naught epsilon naught squared. Okay, so this is the momentum density. This is the average momentum density, let's say, which is being carried by the electromagnetic waves. So you see, the electric and magnetic fields, they have their own, life. They carry energy, they carry momentum. We'll soon see they also carry angular momentum, and they are a system on its own. Just like particles, they have energy, momentum, etc. So does the electric and magnetic fields. They also carry energy and momentum, and that also has a conservation principle. And the conservation principle takes care of both the mechanical energy and momentum as well as the electromagnetic, like in the E and B fields. That contains energy and momentum. When you put them together, then the total energy and the total momentum, that is conserved. Okay. Again, modulo, there can be some current which is flowing out. Okay, they have their individual currents also in terms of the electric and magnetic fields. So that is also possible. So it's just like any other conservation equation. There can be a density and there can be a current. Okay, so here, therefore, we see that the electromagnetic waves carry momentum as well, and that average momentum density is given by this expression. So let's say now this electromagnetic wave is incident normally on a surface and it gets absorbed. If it gets absorbed, then it basically delivers its momentum onto the surface. And if it delivers its momentum onto the surface, let's say, then that, let's say in time delta t. So of course we are considering average here. This average is over a much smaller time period. So if there's a if there's a let's say over a large time delta t, the total momentum change that would happen, which is going to be the momentum that will be getting imparted on the on the surface on which the wave is incident normally and getting absorbed. That will be given by the momentum density times the volume element. So as you can see, A times C times delta t. So this is a little bit of a volume element. So the momentum density, if I multiply by a volume element, I will get the momentum. So this is the momentum change that is happening over time delta t. Okay, this wave is propagating at the velocity of light. So this is c. Okay, so in time delta t, this is the momentum change that is happening. So basically now, if I consider the pressure that is being imparted on the surface on which the electromagnetic wave is getting absorbed, then this is just the rate of change of momentum per unit area. So if you just now plug in everything, we'll get this half epsilon E naught squared. Sorry, this is E naught squared. Half epsilon E naught squared. This is the amplitude square. Okay, and if you check the expression for intensity, intensity half epsilon E naught squared. So this is just intensity by C. I'm sorry. This is intensity by C. Okay, this is intensity by C. And this pressure, which is imparted by the radiation which is absorbed by a surface, I'm assuming complete absorption. Okay, so this pressure that is being exerted, it's called radiation pressure. And it has very interesting physical consequences. Like, whenever electromagnetic wave is incident on something and gets absorbed, then, there's some radiation pressure on it. In fact, there are some designs that people think about, designs of spacecrafts where you can put some sail and, there can be radiation that is incident from the sun or something, which is incident on the sail, and that can give you a pressure and that can help you propel, actually. Okay, these are some ideas that people use using radiation pressure. This has a very practical consequence, the radiation pressure of electromagnetic waves. That is happening all because the electric and magnetic fields themselves carry momentum. Okay, and that there is a momentum density associated with the electric and magnetic fields themselves. Okay, very good. So now the final topic is basically conservation of angular momentum, and that's not very far from the discussion of conservation of momentum, because if you take the local statement, if you consider the local statement of the conservation of momentum, and then basically take a cross product with x. Okay, because as we know, x cross momentum is basically angular momentum. Okay, so with that idea, we can take the conservation equation for the conservation of linear momentum, and then cross it with x to find the conservation of angular momentum. So if we cross it with x, that is basically I have written down in the epsilon notation, that cross product. Okay, so we have to take epsilon ijk xj, and this k is the free index here every term, and this one, as you know, is the divergence of the Maxwell's stress tensor. Okay, this is the term, and this also has a free index k. Every term has a free index k, and that k index is contracted here. This j is contracted here. Okay, so that basically we can take this equation. And now this thing can go inside the time derivative because this is an independent variable, and therefore this term and this term immediately gives me this is the mechanical angular momentum density, and this is the electromagnetic angular momentum density. Okay, these are just nothing but x cross the momentum density in both the cases. Okay, but here there you have to do a little bit of work, because here there's a divergence and you cannot take the x inside easily. Okay, so because there is a divergence, you cannot take the x inside easily. So let's say I took this x inside, and let's see what I get. Okay, so if I took this whole thing inside, there will be, of course, the derivative acting on the x. There will be a term where the derivative acts on the x. So let us see what that term is. So we start from the whole thing inside and act the derivative. So when the derivative acts, there will be one term where the derivative acts on the Maxwell's stress tensor, and that will be this term, and that is exactly this term here. Okay, that we were talking about. And then there will be an additional term where the derivative acts on the xj. Okay, because it acts on the xj, then del m xj is going to be delta mj. That we know for sure. Okay, because that is going to be delta mj, then this mj is going to be symmetric. So this, this mj, this will contract this m index with the j index. Okay, because the j index was the one carried by the x, the m index was the one carried by the divergence and the Maxwell stress tensor. But now m has become equal to j because of this derivative action. Because of this, there's a delta. There's a delta. You have to make them equal and take the sum. That's what you have to say. You have to do. Okay. So now if you do that, then this index you see becomes this m index becomes the j index. If you perform the sum over the m index, then this becomes the j index. And once this becomes the j index, we see there are two indices of the epsilon that are contracted with the two indices of the Maxwell stress tensor. But this is completely antisymmetric. So if you exchange these two indices, you will get a minus sign. And if you exchange these two indices, you will not get any sign. Therefore, this quantity is minus of itself. Okay, this quantity is minus of itself. We can exchange these two things and relabel them. So you will find the same quantity, and this is minus of itself. So this is basically 0. Okay, this vanishes. Okay, so if this vanishes, then this term, which was present here in this expression, is identically equal to, if we took this expression inside, it will be the same thing. Okay, so now we therefore have a statement of conservation of angular momentum. So here we have taken everything inside. Now this term is taken inside. Okay, this term is taken inside, and the signs are adjusted. There was a sign here which can be adjusted with the sign of the epsilon. Okay, you can absorb this sign into the epsilon, this additional sign, and once you do that, then you can write it in the form. This is like angular momentum density of the mechanical angular momentum density. This one, where this is the this is the linear momentum density of the electromagnetic wave. Then this x cross that is the angular momentum density of the electromagnetic wave. This one here. Okay, and finally this term here, which is t cross x in some sense. There's a k and j. So this term, which is k and j, this k, and then there's this j, this contraction. Okay, this term is nothing but this index of the two index quantity, which is in cross product with the x. Okay, so it is sometimes denoted in this way with the double arrow notation. It is sometimes denoted in this way, that this index on this side is crossed with the x. Okay, that is how it is denoted. Okay, and then this two index quantity is basically the electromagnetic angular momentum current. Okay, this always had that interpretation. The divergence term always had the interpretation of a current. Okay, it's the divergence of a current. So this is angular momentum current density. Okay, I forgot the word density again. Current density. Okay, so this is angular momentum current density, and you can write it in this way, and then you can write a angular momentum conservation equation in this way, where this is linear moment, where this is mechanical angular momentum. This term is mechanical angular momentum, and this term is simply r cross e cross b, or x cross e cross b. This term is that. This is the electromagnetic angular momentum density, and this one is angular momentum current density. Okay, so this angular momentum current density can be derived out of the Maxwell stress tensor also. Okay, so this is the conservation of angular momentum. Now, to finish this discussion, again, this has been a long discussion, so just to finish it quickly, let me discuss this particular example again from Griffiths, which is also very interesting. It is on page 375 in Griffiths. Okay, you can try to look at it. I will actually design a problem based on this. I'll just discuss it very briefly. So here, what you have is, you have three cylinders. There's one cylinder in the middle, which is around which, there's a wire which is wrapping around this. Okay, so this is like a solenoid. The cylinder of radius r, capital R, that is like a solenoid. Okay, and you have magnetic fields which are inside the solenoid. Okay, there are some magnetic fields which are inside the solenoid. Outside, you can say that there are no magnetic fields. Okay, there are magnetic fields only inside the solenoid. Okay, so now there is another two cylinder. One is this plus charge cylinder sitting inside, and the other is the which is of radius a. A is smaller than r. Okay, and then there is another minus q charge cylinder which is sitting outside. With that radius is b, and b is greater than capital R. Okay, these are two charged cylinders. So there is electric field between, in the radial direction between these two cylinders. Okay, that's the scenario where now some current is flowing and some steady current is flowing. So there's some magnetic field inside the solenoid, and there are some electric field inside here. Okay, and so in this situation, if you suddenly start to reduce the current, let's say you are starting to reduce the current. Okay, then this reduction of the current will essentially change the magnetic field, and the changing magnetic field. So the magnetic field, the strength will start decreasing, and the changing magnetic field would cause a electric field to be generated along this region, and that electric field will act on this charged cylinders, and this electric field will start to rotate. They will impart a torque on these cylinders, and because of the torque, these cylinders will gain angular momentum and start rotating. Okay, the cylinder inside, if it is free to rotate, then this will start rotating. Okay, so just by reducing the current, you can induce these cylinders to